then we go to the last presentation of Martijn Bakker. He spent, I think, more than 10 years on predicting demand, and he is now using it for predicting also bursts and other calamities, and he will finalize this session. Go ahead.
Thank you very much, Luc, and thank you all for still being here at Friday afternoon. I'll try to keep it short because we all want to go to the drinks, and but still I think it's an interesting presentation showing an example of an intelligent water system, an example of what an intelligent water system also can be. And what it actually can do, what kind of benefits it can give for a water supply system in a financial way, but also in a water quality way. Let's see. So what I will be presenting is actually a control system for water supply systems. To give you an idea what that control system is, I will first tell something about the history of automation of water supply systems, and then go into the differences between a conventionally controlled system and model predictive control systems. I did some research to find out what those differences are, and I did that research at a number of full-scale water supply systems. And I will show you the results and end with some conclusions. When we look at water supply in the Netherlands, you see a distinct between the surface water companies and the groundwater companies. When you look at surface water, it's typically that they have rather complex water treatment plants. Because the water is more polluted, and therefore you need more sophisticated treatment processes to make the drinking water out of it. But you see also quite a large scale. Just a rough figure, about one treatment plant serves about 500,000 people. It's a very rough figure. Just to point out the differences to groundwater systems. In general, those water treatment plants are much simpler because the raw water quality is a bit better. So you don't need really sophisticated treatment processes to make drinking water out of it. And also the scale of those water treatment plants is much smaller. It started at that the water supply was a municipal task, and each municipality had its own water treatment plant, and that created a lot of small water supply systems. So a typical number of customers served by one treatment plant is about 10% of compared to a surface water system. Well, why I'm telling you this, I think everyone will know this. The scale and the complexity of the systems has influenced the way in which the automation of the system has evolved. When you look at the surface water facilities, they only started to complete automation, to unmanned control of the systems. I think it was only about 10 years ago that the first systems were actually running without manual control of operators. And that's because as I said, the treatment plants are complex, and a very reliable control is needed to have it the desired level of control. And before, let's say 10 years ago, that was not really possible, and was also not economical feasible to build such an advanced control system that could actually control a surface water treatment plant. when you compare that to groundwater systems, they started automating the flow control much earlier. And that's because they had rather simple processes, so also the automation of that treatment plant was a lot easier. And another thing is that because of the smaller scales, the labor costs were relatively higher. They had more operators per customer. So I think even at least before I started working, all of the groundwater treatment plants were already running unmanned and were already automated. However, when they started automating those treatment plants, they applied rather simple and robust control systems, like typical level control systems. And only, about 15 years ago, the first treatment plants were, the first more advanced control systems were implemented also at groundwater treatment plants. So that led to the situation that at the treatment plants, a lot of them have very basic level-based control systems, and a number have more advanced model predictive control systems. To show you the principles of the differences between those control systems, first I want to say, give a short explanation about level control. As Kees de Korte also already pointed out for the control of sewer systems, there was a good explanation of a level control. When the level is dropping, the pumps will be running, or in a sewer system it's just the other way around, but the principle is exactly the same. There is an actual measurement of what the level is now, and that actual measurement at this point of time directly controls whether how many pumps are running or at what speed. Here's an example of a SCADA screen. These are raw water wells of a treatment plant. Each raw water well can be put up to one of the commands, and based on the level, the commands will be switched in. When the level is dropping, the more commands and the more raw water wells will be running. And when the level is going up again, each command will be switched off, and the production flow is going down. But the key is that the actual level measurement directly controls the production flow. You can use more advanced model predictive control, and in that case, not only the actual level in the clear water in the reservoir determines the production flow, but actually you make a prediction. A prediction is being made of how much water will flow out of the buffer, out of the reservoir, and then the algorithm will calculate how much water has to be put into the reservoir to keep it between an upper and a lower boundary for the next typical 48 hours. So the response to a level for about, let's say, 50% will be totally different if that occurs at 12 in the midday or at 7 in the evening, because the prediction will tell you if it's a problem to have a 50% level at this time, or if it's not a problem. There are a number of groundwater systems and also surface water systems where model predictive flow is actually controlling the system at this moment. I I want to do some research what the actual differences are between those two kinds of control of the system. And therefore I took 5 of those full-scale water supply systems where the model predictive control is already running. Because I know at those systems the level control system is still there, is still implemented, and it's there as a backup control for an eventual failure of the model predictive control. So that's an ideal situation to do the research, because we could decide to switch off the model predictive control for 1 week, and then it automatically switched back to the level control. And after that week, we, of course, turned on the model predictive control again. And that gave us 2 data sets of model predictive control versus level-based control. Those are the water supply systems at which the research has been done. I won't bother you to explain all the treatment steps in it, but maybe it's nice to have an idea of the number of people being served by each of those systems. So you see that it's a bit of a variety of the size of the system, but in general they have rather big size, and it's just real full-scale systems. It's also nice to see that some of them are, let's say, rather simple, just having 1 reservoir and 1 supply area, but there are also more complicated with more treatment plants and more supply areas. To give you an example of one of the systems where the research has been done, this is the system of Flevoland. The model predictive control is controlling all the assets where the red circles are around. So the production flow of these 2 production facilities are not controlled by the software, by the model predictive model, and also not the distribution pumps pumping it directly to the customers. So in this example, only about 20% of all the electricity which was consumed by the total system was actually directly controlled by the model predictive control system. That's a number just to keep in mind. To give you an example what the difference is, we look at the trends of one of the reservoirs. On this side, you see the week with model predictive control. The controller was configured to make use of cheaper energy during the night. Let me first say what all the lines are. The green line are the water demands in the area. The blue lines are the level in the reservoir, and the red line is the intake flow into the reservoir. And this is 1 week, and this is another week. And you can see here that it was configured that it should make use of cheaper energy during the night. So therefore, during the night, higher intake flows are controlled, and during the day, lower flows. And this is how it works with the model predictive control, and this is what it looks like with the conventional control. And you can see that there's a lot more fluctuation in this week, and also that that occur higher maximum flows, and that the lower flows occur at moments also when the electricity is more expensive. Another example. The round circles again are where what is controlled by the model predictive control. And those are all assets which actually consume energy. And in this situation, about 70% of all energy which is consumed by the system is actually controlled by the model predictive flow control. And when we look at this facility, again the same curves in which the lines mean the same. You can see here the green line is the distribution flow flowing out of the facility. You can see in the week with model predictive flow control that it's a rather constant line, and you see that the amplitude is much higher in this week, and this is caused by the fact that the conventional control doesn't optimally use the reservoirs in the distribution area, and that results in extra flow changes in the treatment facilities, and also in lower flow during the night when the energy is cheaper. So I'll come up now to the summarized conclusions, because all of those 5 systems really generated lots and lots of data. I think I need that iPad to make information out of it. I tried to summarize this in a number of graphs. This graph is showing the energy consumption in per cubic meter. You see here in the first system where there's a rather small difference between the level control and the model predictive control, but that is caused because the difference is related to the total energy consumption, and as I said before, in this system only 20% of the total energy consumed is actually influenced by the way of control. At this system it was 80%, which was, I mean 70%, which was influenced by the way of control. So the savings of model predictive flow control at this system were much bigger relatively than in this system. If you take the average of all those systems, there was about 3% less energy consumption, and because more was consumed during hours when the energy is cheaper, the cost reduction was about 5% of the energy used. I also looked at the water quality, and I saw that on average the turbidity rates and the particle numbers were about 20% lower for the systems controlled by model predictive flow control. And this gives you an idea about how much use the reservoirs are used in the control. I think I just said that, and because of the time I will speed up a bit. So putting model predictive control into operation, of course, also costs some money. However, when you compare that to the benefits, and when you only look at the benefits for the energy costs, then the implementation will have a return on investment of about 2 to 4 years. And of course, that very much depends on how much of the water supply system will actually be influenced by the way of control. So the more part of the system you will control with model predictive control, the higher the benefits will be, and also the shorter the return on investment. Well, that's only the financial side. When talking to the operators which use the systems, they say, well, the biggest value for me of using this model predictive flow control is more that I have a stable operation. I don't have to worry when the temperature is going up. I can rely on it. I have overview over the system, and I know I have less pump wear, and so that are the facts which are for the operators even more important than the reduction in costs. I'd like to thank, first of all, the utilities who actually made it possible for me to do the research. So VTENS, Brabant Water, and WML actually switched off the control for 1 week and let me have all the data. The research I did in the Disconto project, which is a project with a number of utilities, the university, and some other parties, and which it's actually funded by agentschap.nl. I thank you all.